Hi, this is Brian Nett with HowRadiologyWorks.com. If you're new to the channel, please subscribe below and consider clicking on the bell icon. That'll give you notifications when we update new content. And in general, what we do here is we provide short, bite-sized videos about key important concepts in radiology and how the radiology equipment works. And what we're talking about today is just the definitions for digital X-ray imaging, but these are more, the context is digital X-ray imaging. Again, these are more broad in terms of the signal to noise ratio and the contrast to noise ratio in the image. And they're very important things to quantify about how well our images do at allowing us to see the area of interest. For instance, if we'd like to see a tumor in the liver with respect to the liver background, how well can we see that tumor? We'd like to quantify that. So that's at a high level what we wanted, why we wanted to define the signal to noise and the contrast to noise ratio, and just what do those mean in our imaging. So we have noise in our X-ray images. That noise is due to quantum noise, and those are random fluctuations in the image that make it more difficult to interpret the images. So in the case of X-ray, those are due to photon statistics, and when a higher radiation dose is used in general, we have fewer fluctuations, less quantum noise in our image. But just in general, there's a trade-off, right? We can think of this being lower dose images down here. And now you can't differentiate anything, for instance, inside of my hair. So here you can see these little structures inside my hair. Those are completely gone here when we go to the lower dose image. But you do see that you still can see my eye, you still can see there's a pupil in there, you still can see my hand. So it all depends on what your task is in terms of the appropriate radiation dose. But in general, what we want to talk about today is just one way we can quantify that is the signal to noise ratio of your image or the contrast to noise ratio of your image. And in general, you can think if you take an image, you have a background, and then you have the thing you'd like to see. For instance, in this case, you can see these little discs in our image. And the question is, how well can we see those with respect to the background? That's typically the question of interest. So we have these discs in our image, and our ability to see them will depend on how large they are, and it will also depend on how bright they are with respect to the background, or how dark they are with respect to the background. So, in general, you can see this is an example from a CT use case where these are 0.3% different, 0.5% different, and 1% different in their X-ray attenuation coefficients. And then the question is, if we have an image like this, where we have these regions, and then we have a background, how can we define the signal to noise and the contrast to noise ratio? So we could take, for instance, take part of an image like this and kind of think about blowing it up and looking at the values inside of here. We can do things like measure the values in a region. We can measure the mean value in that region or the average value in that region. And then we can also measure the standard deviations in regions, for instance in the background. And that's how much the pixels are changing. Standard deviation is how much the pixels are changing from one pixel to another within that region. And that can be used to give us an estimate of the noise in the image. So in general, if we talk about, say we take part of that image there, and we talk about drawing a line through that image, then you can make a plot like this, which shows a couple different regions. It has a background region and it has two regions that have different intensity inside of there. And then the question is, you can see there's some noise here on the background. And what is the signal to noise here? And what is the contrast to noise here? And we just want to look at this and kind of get a rough idea. In reality, we'd be doing measurements, like I said, of the mean value and of the standard deviation. But if we look, the question is, how much is the signal to noise? So the signal in the units that are reported here, so for instance, say these were CT number units, or these could be units on an X-ray detector. The signal, for instance, is 150 on average here in this region. And the signal on average here in this region is 100. And then if we look at the noise, we can see the noise standard deviation is around 10 units. You can look here, around 10 units on either side is about the standard deviation. That's the definition of the standard deviation is used in the background. So the definition of the SNR is the average pixel values in that region divided by the standard deviation in the background. And then the definition of the contrast to noise, which a lot of times is actually more what they're looking at, is the contrast between this region and between the background region. So in that case, we'll take the average difference, the contrast of 150 minus the 100 in order to get that contrast. In this case, we're just talking about the signal. So what's the average measured signal? And then here we're talking about the contrast, so the difference between the measured signal and the two regions that we're looking at. So here, our SNR in this case is about 15 because we have a standard deviation in the background of about 10, and then our average values were about 150, so that SNR is about 15. Meanwhile, the CNR, if we take that 150, we subtract the 100 in the background. Sorry, we subtract the 100 in the background. That gives us a value of 50, and then we would divide that by that 10 noise. So our contrast to noise ratio is 5. So that's more often what they're concerned with, is how well you can determine the contrast from the background. But at a high level, that's all I wanted to cover for today, is the SNR, signal to noise ratio, and the contrast to noise ratio, and what the definition of those units are, and why they're important in quantifying the image quality. So this was discussed in the context of X-ray imaging, but those concepts are universal throughout a radiology department. And in all of the imaging modalities, we're interested in the concepts of signal to noise and the concept of contrast to noise. So again, this was Brian Nett with howradiologyworks.com. Please stop on by the website. We have free courses there, as well as courses you can register for. For instance, for CE credits for radiologic technologists. Thank you. Comments down below. Let me know what your favorite part about digital X-ray imaging is. If it's just the fact that you don't have to develop film anymore, or specifically, what's your favorite part about this digital X-ray imaging? And also, hop on over to howradiologyworks.com/digital X-ray, and you can see, in that case, we have just a one-page cheat sheet. Just download that. You'll have it at your fingertips. If you have any questions about the content here, you can use that to refer to in the future. Thanks a lot.